So I'm just going to go ahead and introduce myself. I am Casey Green. I am your moderator today, and I have Chuck Powell with me. He's going to moderate our chat and our discussion when that time comes. Welcome to the UAS SIG 1. I love the title of this, by the way. Whoever came up with it, you know, because I was once in that spot where I got a drone. What do I do next? So this is great. We have a lot of great speakers, and let me introduce the first one and share a little bit about him. Okay, so our first speaker is David McKittrick. David is training and outreach manager at Blue Marble Geographics in Hollowell, Maine. A graduate of the University of Ulster in Northern Ireland, McKittrick has spent over 30 years in the field of GIS and mapping, focusing on the application and implementation of spatial technology within a wide variety of industries and vertical markets. McKittrick has designed and delivered hundreds of GIS training classes, seminars, and presentations, and has authored dozens of articles and papers for numerous business and trade publications.
Well, thank you, Casey.
Oh, we were very excited to have you, David.
That makes me sound awfully important. I don't know if I can live up to that bio. I think you need to make me a host or co-host, I believe. There we go. You got it.
Yeah, making you a presenter.
Excellent.
Make
You should be seeing my screen now. I'm assuming you're seeing my screen?
Yes.
Perfect. Excellent. So thank you for the introduction, and thank you for the invitation. Thank you for the opportunity. As Casey mentioned, I am in the state of Maine. I don't know if I take the award for the furthest distanced from the actual presentation, the actual conference. I don't know. I'll award myself that one. Great to be here. Great to be in the presentation. We'd love to be there inside, obviously. In the circumstances we're currently under, it's difficult. So we do the best we can. And hopefully what I cover here, got about 20 minutes. I want to throw this question up on the screen and hopefully answer it as well. Got a drone now, what? Mapping with your UAV. And this presentation came about because of a question I was asked. I was at a conference in London a couple of years ago, and somebody came up it was a drone conference. Somebody came up and said, "I've got a drone. What do I do?" So, wow, there's a good question. let's have a chat. So we kind of continue with that theme, and I'm going to try to answer that question, obviously in the context of mapping. We're going to take a look at mapping with your UAV. Now, let's make sure my slides advance here. Take a look first on my agenda. Before we do that, there's one of my colleagues sending his drone up in the little visuals here. Going to begin by telling you what my objective is. I have 20 minutes of your time here, a little less now. And I'll start my presentation by going over what I hope to achieve in that 20 minutes. It's more than just here's some bullets, here's some interesting talking points. I'm actually going to show you something. I'm going to show you some real data. I'm going to show you a real scenario. You know, I've got my sleeves rolled up. I have my clock in front of me, so I will not overshoot. That's kind of outlining a very ambitious agenda here. I'm going to start by addressing the question, what is structure from motion? Structure from motion is well, I'm not going to spoil the plot, but it's a image analysis process, basically. We are going to essentially take drone images, and from those drone images, we're going to reconstruct the three-dimensional environment. That's kind of layman's introduction as to what you're going to see in the next 20 minutes. We're going to ultimately generate a point cloud, and we will see this. We will actually see this in real time. We're going to generate some data, or pretend to. Many of you may be familiar with this data structure. Maybe you may have used this. If you haven't, I'm sure you are familiar with Lidar. I'm sure you've used Lidar for whatever 3D analysis, feature extraction, DEM creation, all that fun stuff. We're going to do a quick look at what's the difference. You know, why would I think of generating my 3D data using the technology you're describing as opposed to using Lidar? And we'll take a look at what the differences are. There are benefits to both, and we'll take a look at those, take a look at some of the limitations as well. Then we'll take a look at structure from motion in action. This idea, again, I'll introduce this with a slide in just a few minutes. We'll actually take a look. We're going to switch from PowerPoint. You'll have the obligatory half dozen or so slides to get things rolling, but we're going to take a look at some software. We're actually going to go through a simulation, and we're going to do some analysis. We're going to generate a point cloud first of all. We will then, just to make this a little more meaningful, yes, fun to create 3D data. I can't. It's really fun to play with that, those fly-throughs, etc. But to make it meaningful in a semi-simulated situation, we'll first of all, within our point cloud, identify those points that are likely to be ground. And now this gives us a higher level of intelligence, allows us to move towards the idea of analysis as opposed to just visualization. Obviously, next step from that, once you've identified ground points, we'll generate a DTM, a bare earth model. And final, we'll generate some contours. So I like to remind people when we finish, as I will in about 18 minutes, we're going to start this entire process with just some photographs, some images, some pictures. And before we get there, we will obviously take a look at the process and the procedure that's required for doing that. Again, formally outlining my objective, the transformation of overlapping drone collected images into a three-dimensional geospatial model of the target area using, as I've mentioned, structure from motion. And brief. What is structure from motion? What are we talking about here? Well, very crude illustration on the left side of my screen here. Let me bring up some bullets to describe it a little more clearly. It's an image analysis process. The little squares you see in my graphic represent images captured by a drone. As you can see, there are multiple locations. The drone moves. The drone's on a flight path. It's capturing images. The little dots on the ground represent recognizable features, if you like, something that's identifiable in the pixel pattern, a curb or a manhole or something that can be distinguished from what surrounds it, because the process essentially will identify that collection of pixels and look for the same collection of pixels in an adjacent image. And if it finds them, it says, well, I can recognize these as well, and maybe another image and maybe another image. And as it does that, it develops this perspective from multiple locations where it can identify where that is in three-dimensional space. I sometimes use the very crude analogy of your eyes. When you look at something with your eyes, with one eye covered, you're seeing a very singular representation of whatever that feature is. Bring in a second eye, and you get that depth perception. We don't think about it, but that happens. We can see how far that thing away is, that object is from our eyes, relative to what's beyond. Now, imagine you had multiple eyes looking at a feature from multiple perspectives. Again, that's the basis of the technology we're going to be taking a look at. But the bottom line here is it's image analysis for reconstructing the 3D environment. In order for this to work, if you're interested in doing this, by the way, if you have a drone, absolutely, you can send your drone up, send it on a flight pattern. It doesn't require anything else. I'll show you the raw material in a second. But you have to have texture. You have to have something identifiable. You can't send your drone over a snowfield, where I'm in Maine, that's common, or a desert, maybe more appropriate for Arizona, or water. You're not going to see those patterns. You may also encounter situations where the patterns change. Water. As an example, you have wavelets on the water, you have a boat that's going across the water, a car driving along the road. Those are considerations. If your drone is on a flight path that takes it over a certain area, you need to make sure that there's no moving objects. Otherwise, that feature that it's recognized will be in a different location and possibly have a different structure. So a little bit of pre-planning, kind of common sense applies when you're embarking on this process. You have to have overlap. As I mentioned, we're talking about multiple perspectives. Image overlaps, we're looking at least 60%, usually more. You'll see some examples when I bring up some data where the same feature is visible from multiple perspectives. So having that overlap is essential for what we're about to show. And again, recurring patterns of pixels. That's all we need. We need something that's identifiable in those multiple images. And thereafter, it's a simple process of triangulation to recreate the identifiable objects in a 3D environment. Now, there's a lot of very complicated stuff goes on under the hood. We don't need to worry about that. What we see at the end of the result, at the end of the process, is a reconstruction, initially as a three-dimensional point cloud from which we can derive additional products. Now, bringing this into the context of why we're all here, this is a GIS conference, geospatial. We can construct the 3D environment in and of itself. In other words, we can build a 3D model just based on arbitrary locations. But to make this more meaningful and to make it more useful and more applicable, you can also apply ground control. Again, requires some pre-planning. You head out beforehand, you establish your targets, you survey them, you know what those coordinates are, three-dimensional coordinates, and you can plug those in, giving you a higher level of precision in terms of how that ties into maybe existing surface models or your existing terrain data. As again, it's not required, but it certainly will improve that accuracy. Now, I will, when we bring up the software, show you a few other options for post-processing your data to improve its accuracy, but certainly it's something you should prepare for before you send up your drone. So again, by way of paving the way, we're sending our drone up, we're flying a pattern, we're collecting simple images. Inherently, those images do not have any geographic intelligence except for the simple fact that they know the location where they were taken from. And if they know where they were taken from and they can identify those, I keep using the phrase, identifiable features, that 3D reconstruction can be performed. Now, as I mentioned at the start, Lidar, we know Lidar. Everybody consumes Lidar. I use Lidar daily. The differences between Lidar and you'll see the term FODAR. I don't like the term photogrammetric point cloud. Basically, that's been adopted as kind of a pet word for what we're going to generate today. What are the differences? What distinguishes the two? Well, fundamentally, they're different in how they're created or collected. Lidar is active. The simulation or the little graphic you see on the left shows an aircraft, the scanning process, scanning the underlying terrain, underlying buildings, etc. And it's generating data in real time. It's getting those laser returns and it's creating that point cloud on the fly, land your plane, land your drone, upload your data, and you're good to go. You might want to do a little processing, classification, cleanup, noise removal, etc. But at least you have data right off the bat. With FODAR, it's different. Your raw material is imagery and it requires a significant amount of processing. So there's more kind of on the end of the process, or the second phase of the process, if you like, in order to get meaningful data. Both have value, as I mentioned. The value for Lidar, obviously wide coverage. You can get a lot of data over a wide area depending on the hardware you're using, whether it's a fixed wing aircraft, piloted aircraft, or even a drone. The fact that your data is ready in real time. But we tend to find that the FODAR, the photogrammetrically generated point cloud data, is more accessible. And let's look at some of the reasons why. Distinctions between Lidar and FODAR. It says flight planning required for Lidar, and that's based on the assumption you're sending up a manned aircraft. That's no longer the case. We know that. Drones can be deployed with all of the necessary hardware to collect Lidar as well, but still, it does require flight planning, significant flight planning. It also requires optimal conditions for your flight, etc. For FODAR, it's a little simpler. You're sending a simple drone up with just one requirement in terms of the hardware, and you can see that on my second line. It's a camera. You don't require a laser scanner. You require a camera. Taking those images from multiple perspectives. That's all you need. You're bringing up my third line here. It's a lot less expensive. Anybody can do this. I mean, as a company, the company I work for, we have been able to collect this data and process this data. We could never have done that with Lidar. We don't have the resources to acquire Lidar, but we can certainly generate 3D data using this process. As I mentioned, the process for Lidar is typically real time. Gives you clean, sharp data. A little cleanup obviously will be required, post-processing, but at least you're at an advanced stage as far as that's concerned. Whereas with FODAR, you don't really have data to begin with. You need to create the data based on what you collect, and that is what we are going to do in just a second. One of the important distinctions, and I'm not sure how important this is in your part of the world, certainly where I live here, state of Maine, 90% of the state is forested. And people get into this, like, I can buy a drone, I can generate DTMs, blah, blah, blah. If you're dealing with areas where there's vegetation, where there's canopy, again, knowing how this works, you're looking at what's recognizable in a series of photographs. The photographs will capture the tops of the trees, very sharp and very clear images. It will not recognize the ground in those situations. So if you're hoping to get a ground model, a decent ground model, where there's areas of a lot of vegetation, FODAR simply will not do that for you. It just doesn't have that capability. Whereas we know Lidar, based on that technology, has the ability to penetrate through canopy, even the densest canopy, to capture what's underneath. So that might be a deciding factor in what you choose. I just saw a chat message coming through there. I didn't quite catch it. Maybe somebody could ask that one later when I'm finished. It just disappeared from my screen. Let me keep going for now, and maybe questions at the end. And that's probably the best way to answer any questions. So as I said, I'm about 10 minutes into my presentation here. I'm going to actually take a look at this in action. I've got about 9 minutes now to show you this process, and I'm going to use a piece of software. Disclaimer here, this is the software that my company develops. This is Global Mapper. Some of you may be familiar with it. Global Mapper has an add-on component called the Lidar module. As it implies, it's for working with point cloud data. And a feature of that is a tool called pixels to points. Pixels being images to points, point cloud. We're actually going to simulate the use of this tool ultimately within the 9 minutes I have available to show you how we can go from drone images to contours. So before we begin, let's take a look at the data. Just geographic reference, by the way, just some data I happen to have. This is the state of Vermont. This is a farm, a little farm area. We're going to generate some contours in this area. The images themselves, here's my drone images, obviously preloaded here. They appear as little icons. I can click on one. It will show me the image. It will show me the approximate coverage. This gives me an initial view of that image. Now, if I click on a field, let me grab and drag this out of the way just a second, looking at something recognizable. Here we have this barn, this farm building, and you're looking at it from a top-down perspective. If I click the next images, you're looking at the same farm building. This one over here, again, slightly different perspective. Maybe if I choose one a little further, oh, I'm too far away. Let's try this one. Oh, yeah, you can sort of see it. You get the idea. We're looking at this farm building from multiple perspectives. We're looking at this from different vantage points, if you like. And that is the essence of how this process is going to work. This initial QC that I can do just by showing my overlap will prove to me and confirm that I have the necessary data to perform this analysis. So let's take a look. I'm going to fire up the tool. I'm just going to go through the motions here. I will not actually do it. This is like a cooking show where I'll show you the ingredients and I'll pull one of the oven I prepared earlier. I'm going to add my points just to show how that would work. I'll add the loaded picture points I have on my screen. Now, this is where we would set up the necessary parameters, identifying things like ground control points if they were visible in an image. Just waiting to refresh my screen here. This is always the issue with a live demo. We'll refresh. There we go. So there's my first image. There's, selecting these images randomly. Again, we get a preview. We can zoom in. Looks like this is probably the guy actually flying the drone here. We can zoom in. We can see those features. If there were ground control here, a red X or a white X in the ground, whatever you've placed there, you can tag that. Your ground control points would be managed here. If I had them, I could simply say this ground control, here it is right here. That would make sure that that location that's identified in those images, multiple images, would be tied to that XYZ location precisely. Few settings here in terms of how it's processed. Harmonizing color, for instance. If your drone is flying on a flight path and between those flight paths, maybe a cloud blows over the sun. So the colors are literally going to be different. Shadows that were there before are no longer visible. There needs to be a way for Global Map, for the engine basically, to determine which image to use as the basis. In other words, that's a base image I use for the colors, and you can define that by harmonizing the color. For your other settings pertaining to your camera, etc., the output files that we will generate if and when I hit run would be the point cloud, but we also, as a byproduct, get a few additional files. I'm going to take a look at these in a couple of minutes. We get an ortho image. It's a top-down view, basically. We get a 3D model or a mesh as a byproduct as well. This is the eye candy. We're going to take a look at this one just a second. So I got about 5 minutes left to generate some contours, so wish me luck. I'm going to close this. And again, as I said, like the cooking show, I'm going to turn off the base image. I'm going to show you one that I prepared earlier. First of all, the point cloud. This point cloud visualized by a shader pattern here. I'll change the shader. Let's view by intensity. As you can see, we've got various parameters. This is now a reconstruction of that area from the analysis process. You can see that in 3D. This is the raw material that was generated through that image analysis process. I've just opted for an alternative method for visualization. You can choose whatever way you want to view this. By classification would be an interesting one. There are no classes present. There's no distinction between what's a ground point and what's a tree or anything else, a building. I want to address that in just a second. Another output, as I mentioned, is the ortho image. This is my top-down view. Now, people often assume that when you do this, you're basically taking the original images and you're stitching them together. No, that's not what's happened here. What we're doing and what we're looking at is a gridded version of the point cloud with the colors present. So this is a raster version of the point cloud that I can use for any image analysis. I could generate a geotiff, generate an ECW file, whatever I need. I use the three-dimensional analysis to generate precise pixels in a raster layer. So I'm going back to the raster world again. But by definition, every pixel is correct in terms of its geographic location. That is byproduct number 2. And the final one here is a mesh. Now, this is, again, the eye candy. It looks the same as the ortho image, but this is actually a vector file. And the best way to visualize this is to pop it up in a 3D viewer, and you can see what I was able to generate. Unlike the point cloud where they're individual points, this is now just like a solid surface. It's remarkable to me with those top-down images. I'm even able to see the sides of this building using this process. I can go right down to the road level here. I can see the potholes in the road. So this 3D model was generated as a byproduct for, again, 3D visualization. So back to the point cloud with the couple of minutes I have left. I want to, first of all, within this point cloud, identify which of the points are ground. This is a simple process. Got a button right here in the toolbar for doing that. I'm just going to leave the default settings here. It'll take just a few seconds. It's looking for the geometric characteristics of each point in relation to its neighbors. It's looking for a surface. It's matching neighboring points. And ultimately, based on a preset color pattern, it should show me my ground points. Now, this gives me the basis for terrain analysis, where the raw point cloud itself, yeah, great for a surface model of the buildings and the trees. This now isolates my ground points and gives me the means to generate a raster digital terrain model, a DEM, representing bare earth. I'm going to go through that process very quickly as well. Click OK once again. Just based on the default settings here, I do need to filter the points so I'm not using my unclassified, only my ground points, because that's what I want to isolate for this model. So that's fine. Everything else should be okay. And hopefully, again, within a couple of seconds here, I see a bare earth model. Now, the visualization is a little strange based on my shader. I'm not quite sure why it's using this green color. It should be multiple colors, but that's okay. We can see this texture. We can see the surface represented with this hillshade texture. Without the buildings, by the way. That initial process, removing the non-ground points, left me this bare earth model, which now is the basis for the final step in this process, which I think I'm going to make it before my allotted time is up, to generate some contours. Let's make some 1-foot contours, just for illustration purposes. I don't need to find local peaks. Everything else should be as it is. It'll run through an analysis, basically connecting the dots, and there we did it. We were able to generate some 1 meter contours based on, okay, I went through the process a little quick and I had some of the data pre-canned, but it's not that difficult to envisage sending your drone up, doing your flyover, doing that initial analysis, and I should be, in the interest of full disclosure, that processing took about an hour in the real world. From the drone images to something, the point cloud that I actually used, took about an hour. But thereafter, you have the raw material to do volume calculation, watershed analysis, viewshed analysis, all of those 3-dimensional analysis process. And I remind you now, here we have some contours. We started with drone images. With 30 seconds to spare, I did it. Questions, if you have them. I don't know how the questions are going to be managed in the presentation, Casey.
David, we have a couple questions. We have a little bit of time. So is there a difference between FODAR and SFM, structure for motion, or are they the same thing?
So structure for motion is the process. Structure for motion is how you analyze the images. You're looking at the motion, in this case, is the motion of the perspective of the camera. So that's what the structure for motion is. You're generating structure from multiple perspectives. That's kind of more a description of the technology. FODAR is just a pet term that's used for the point cloud to kind of distinguish it from Lidar. Somebody made it up at some stage. I don't like that term, but I find other people using it, and I find it mentioned in other conferences. So I threw it into my slide, but it's just a description of the a very colloquial description of the data output.
Oh, thank you. We have a couple more questions. I think we're out of time. We need to move on to the next presenter. If you can look at the chat, David, sure. And answer within the chat.
I will do that. Yeah.
Thank you very much, David. Excellent presentation. Up next, we have Nick Beasley. Nick works as a GIS analyst with Terra Systems Southwest in Tucson. His previous work in agronomy, my tongue's all twisted, led him to his GIS field and a master's degree in geographic information systems technology from the University of Arizona. And he's presenting on examining the use of UAV imagery for population and canopy height estimates. And Nick, I'm going to make you the presenter. And mute because my dog is going wild. Nick, are you on mute? I don't think we can hear you. Nick, we still can't hear you. You may have to dial in. I'll send him a message.
Hello?
Nick, is that you?
Yeah, can you hear me now?
Oh, yes, we can hear you.
Alrighty. Sorry about that. I was talking away for a little bit there before you held me back. So
No problem.
great. Can everyone see my screen?
Yes, we can see your screen.
Okay. Great. Okay. So yeah, as you said, I'm currently a GIS analyst at Terra Systems Southwest here down in Tucson, Arizona. And this is part of the master's project, the research that I did for that at the U of A for the GIST program. So getting started here, just a quick overview, pretty much follows a standard scientific paper outline. So getting going with the introduction, commercial agriculture. So commercial agriculture is something that we depend on as a modern society. Anything from most of our food to a lot of our textiles, lots of bioproducts are grown in commercial agriculture settings. And something that farmers have had to deal with since literally biblical times is field and crop variability. So regardless of the size of a field, you're always going to have some kind of variability around that. You're going to have different soil structures, you're going to have different water holding capacities, you're always going to have variability. And one way that growers cope with that is through variety trials. So trying different varieties on certain types of soil and in certain conditions, and selecting the best varieties for their circumstance. And a tool that really has helped, or a set of tools that has really helped farmers in recent years is precision agriculture. There's a number of tools involved in precision agriculture, a number of ideas involved with it, but really it stems from the beginning of GPS. Farmers being able to spatially reference a field, collect data, put that data again in a spatial sort of analyst environment, being able to analyze it spatially. There you go. They can gain a lot of data and a lot of information from that for decision-making purposes. And as the topic of the special interest group is drones, this is definitely a tool that is receiving a lot of attention right now in precision agriculture. So the scope of this study was taken in Marana, Arizona, Double D Farm Partnership. And you can see the field there on the right. It's approximately 12 acres. It's a flood irrigation system, a concrete furrow to the north of the field where the water floods into the field. And then those earthen berms are about 50 centimeters high or so. And they are used to separate the field so the water can be more evenly distributed. And across that field, going from west to east, you can see the number of plots. So in this specific variety trial, there were 13 different types of cotton that we were looking at. So the objectives here, just examine if the UAV with a visual spectrum camera can be used to count cotton seedlings. Examine how multi-angle digital photography can be used to develop the canopy height models. We're going to look at those results and then kind of compare them to traditional, more field-based scouting techniques. And then, again, look at the relationships among the varieties and then also to their harvested fiber yield. So here's a quick, well, kind of a lengthy flow diagram for the methods. We won't go through all of this, but actually a lot of it was touched on just in the previous presentation. Basically getting the field collected data, getting ground control points, ortho-rectifying the images, and then completing object-based supervised classifications. And in this, I did try a couple different techniques, one using just the 3 bands, red, green, and blue, and then also using a green leaf index, which is a way to kind of highlight the green pixel values. And then I just tried a regular 3-band image. Went through accuracy assessment, selected the most accurate image, and then completed population estimates and population density or hotspot analysis. So here is the image that we first took. This is May of last year. And this, you can see the plants are just getting out of the ground. They're just emerging. So they're at that cotyledon stage, which is just 2 leaves coming out of the ground, the 2 first leaves. And it's important for farmers to know the population at this stage. One, they can see how their seeding did, see how if any issues with planting, anything like that. And also it allows them, if they need to, identify gaps, and they can go back in and replant, and the plants won't be too far behind the rest of the crop. Here's a quick snapshot of some in-field data collection. The guy on either side of the slide there is Dr. Wilhelm Van Leeuwen of the Arizona Remote Sensing Center. On the left there, he's got a rover GPS satellite for collecting those ground control points. And on the right there, he's getting ready, creating the flight plan for that drone to go and take pictures. The guy in the middle, that's me, taking some field counts. So basically just collecting plant counts, number of plants, and then also plant height to compare later. There's a quick snapshot of the flight specs. Basically, the main takeaways here, the spatial resolution needed at this cotyledon stage was really small. So we went with a 0.5 centimeter resolution and an overlap of 70%. And a photo, as you may know, it's really the most accurate in the center of that focal point. Everything, as you go away from the center of that photo, it's going to get more and more distorted. And that's why you have this overlap, and you create these ortho mosaic images that basically helps minimize that distortion across a large area and allows you to efficiently and easily obtain measurements. So that ortho mosaic was then run through a classification. And this classified it into the pixels into 3 groups: plant, which is green; shadow, black; and bare ground, which is tan. It did a pretty good job isolating the rows. You do see some false positives here between the rows, and that could be plant residue or just a misclassified pixel. Luckily, with commercial agriculture, things are planted in rows, so we could just shoot straight lines down them, create a buffer, and then select those groupings of pixels that were within that buffer. And I created this, these dots along the field. So that's the results of the methodology of how we obtained those points that represent individual plants. Looking at the canopy height models. similar process in the field, but instead of creating an ortho mosaic, creating those point clouds that again were just talked about in the previous presentation. Creating a digital terrain model, getting that bare ground, and then elevation models, so getting the plant canopy, and using that, basically just a raster calculator to create the digital canopy models illustrating the growth of the plants for the beginning of July and then the end of July. Then lastly, we compared those to infield measurements. So here's a shot of the ground that we used, or the field that when we used to create the digital terrain model. And you can see the buckets there. Those we used as our ground control points throughout the process. And here it is. The plants are beginning to grow. Canopy starting to develop here in the beginning of July. And as you can see here, by the end of July, the canopy is pretty well closed in. So flight specs, pretty similar. We were able to increase the resolution a little bit, excuse me, to 1.1 centimeters. We kept the overlap at 70%. But in addition to the nadir images, the ones looking at a 90-degree angle towards the ground, we had to take these sets of oblique images. And these are at 30 degrees looking north and south, respectively, down the rows. And through those, we were able to complete the structure for motion process and create 3D models. So here's a sort of a zoomed in snapshot of one of the point clouds. Again, this was used, we classified just the ground. You can see a little bit of plant points in there, but we just used the ground and created a digital terrain model. And then here you can really start to see some of the height, the berm versus the canopy there on the right side of that photo. You can start to see how these point clouds do represent 3D objects. Some accuracies, so some results here. Overall accuracy of the image was 86.5%. Just pretty good, pretty standard for these kind of processes. Obviously, you'd always want to shoot higher, but anything above an 85%, in my understanding, is pretty good. Looking at the infield counts, we had an absolute difference of 10.8. So that I think resulted a lot of, some of them had a lot of, some of the plots had a lot of crop residue. And it was hard to get those false positives out of some of those. So when we look at the individual plants, we throw them on the field, this is what we got. It's not real useful to anybody's eye, trained or untrained. You can zoom in again, you can see how accurate and how you did as far as individual plants, but really we have to make sense of this data. Oh, just a real quick, looking at, let's see, the infield population by acre. We were at absolute difference of 14.08% in the infield population estimates versus the imagery-based population estimates. But again, you have to make sense of that. So all those dots, put them into a density map. So basically, each one of these squares represents about 400 square feet across the field. And you can start to see sort of areas that are relatively high and relatively low to one another, which is good. I mean, that might help you identify some areas that are gaps. But really, we want to look at as well what's statistically significant about these areas. And so that's where the Geddes-Ord or the hotspot analysis came in. And if you compare these two images, you can see that in most cases they're pretty similar. These plots, 212, 213, relatively high population, and sure enough, they are statistically high compared to the others. But for example, if you look at 207 here, this middle row, it's blue almost all the way down, so relatively a low population. But when you look at it statistically speaking, it's statistically pretty average. And even here, kind of in the middle on the 207 line on the right, you can see that there is statistically a high concentration of plants here. So this could be helpful for a farmer to go in and be able to then, look and see, well, for example, these 203, 204, did something happen with the planting? Is there something I can do to help get that population up to the rest of the field? So then looking at the 3D models, the digital terrain model. So here is kind of our base image that we use. This is just elevation above sea level. Again, you can see the two berms, those two lighter colored strips there, illustrating that they are a little higher than the surrounding region. And then again, through this basic raster calculator, I was able to create these canopy height models for the beginning of July and then towards the end of July. You can see there's quite a bit more growth. The thing to look at here are these plots 203 and 204. Notice how there's pretty bright yellow, a lot of growth there. And if you look at these 212, 213, not as much growth. They're definitely growing, but not the same rate that these 203, 204. That's something to keep in mind as we go forward here. But just for some accuracy, results, looking at the canopy height image estimates and the measured height in the field. In beginning of June, or July rather, I'm sorry, July 3rd, we had an absolute difference of about 11.3 centimeters. And then in the end of July, we had an absolute difference of 2.9. I think this had something to do with just the canopy being more enclosed towards the end of the month. Just not as much error, misclassified points by having that full canopy. So looking at it, height change versus population. So again, looking at some stats here, you can see there is a pretty definite relationship there with a higher population resulting in a decreased height change. And again, if you look at that 203, 204, fairly low populations as we saw in those population density maps and a really high degree of height change stemming from that. And then vice versa, the 212 and 213, relatively high population and relatively low height change in that month. Again, we'll look at that height change now and compare it to the yield. So again, we'll look for those two sets of numbers. And 203, 204, with that extremely high amount of height change, resulted in a lower yield. And again, 212, 213, having a more of a moderate to low degree of growth in terms of height, actually led to more yield, which makes sense, right? When you're planting a plant, or your plant is growing, rather, it only has so many hours in the day, only so many resources available to it. And so where that plant decides or where that plant is genetically programmed to put that growth and put that effort will matter a lot, whether that's into a fruiting structure or into more of a stem. So to wrap things up, we're able to create efficient methodology for using UAV imagery in precision agriculture. Did create population estimates for 11 of the 13 cotton varieties. We had a little bit of issue discerning some of the rows in a couple of the varieties, and so just to take out a couple outliers, we just stuck with 11. Our accuracy for the image classification was 86.5%. We were able to create some canopy height models used to estimate growth, achieving a best absolute difference of 2.9 centimeters. Results were pretty comparable to field-based techniques. While they weren't exact and there was definitely some room for improvement, it did show the overall tendencies of each variety. And again, so they weren't maybe exact heights, but relative to one another, it did a pretty good job recognizing the differences among the varieties. So we examined those, and then we also looked at the height change and then compared that to harvested yield. And no good science can be done solo. I have definitely some acknowledgments. As stated, Dr. Wilhelm van Leeuwen and everyone else there at the Remote Sensing Center at U of A. Ms. Karen Geldmacher, germplasm specialist for Maricot. It was fun to be out there in the field with her and looking at how she, looks at these different varieties and makes assessments. Dr. Randy Norton, he's director at UA Extension Safford Agricultural Center. He was really responsible for connecting us with Maricot and Karen. He's doing this type of stuff all over the state. And last, certainly not least, Mr. and Mrs. Gary and Billy Dean of the Double D Farm Partnership in Marana. They were always more than willing to let us come around and take pictures and stomp around their fields. So big thanks to them. So I hope everyone enjoyed that. And if you have any questions, I think we have some time. Thank you.
Thank you, Nick. Chuck, do we have any questions for Nick?
No, we don't. I would like to email Nick a couple questions, but I think we're just about out of time, so we need to move on to our next presenter.
Okay.
You bet. Thank you very much. And my email's at the bottom there if you have any lingering questions. Thanks.
Okay, our next presenter is Jack Taylor. Jack has been working as a drone pilot and geospatial technician for Westland Resources for 3 years. He graduated from Embry-Riddle Aeronautical University with a degree in aerospace engineering. He works primarily with drone imagery and 3D maps and models. As a professional photographer, his knowledge of photography plays a large role in his daily work. Thank you, Jack, for presenting, and the floor is yours.
Hi, can everyone hear me?
Yes, I can hear you. So.
Okay, great. I know my initial title says something about identifying problems in drone data and correcting them. Although the story kind of changed in the telling, and I kind of ended up talking a little bit more about Lidar and how we used Lidar in an example to correct some data that was bad. So actually, I'm really happy that David earlier in that first presentation talked about structure from motion versus Lidar, because he laid some good groundwork as to what I'm going to be talking about. So he did an excellent job and kind of already saved me some time, so I don't have to explain the difference between how structure from motion works. So drones in the air and Lidar on the ground. David was talking about Lidar in the air versus drones in the air, and this is going to be taking a slightly different approach. This is kind of an idea that we had been playing with, and we wanted to put it to the test and see what results we got. So I just kind of wanted to take you guys on this process so you can see what applications mobile and ground-based Lidar have in conjunction with drones. So this is the test case. It's just a small stretch of road in Tucson. We flew this corridor with the EV Plus and the SOTA camera, processed the images using a standard structure from motion software, Pix4D, which produced our digital surface model, that 3D mesh, and the ortho photo, the ortho image. And what you're seeing now is the ortho photo viewed from virtual Surveyor. So this is the software we use to process our images and to process and to create.
Jack,
you're having problems with my.
Yes, your mic is going in and out. I don't know if you can adjust that a bit.
Maybe I was on the phone. Maybe the phone connection is not the best.
Okay. This sounds better. Whatever you just did sounds a little better. So. Okay.
Well, yeah. Let's go with that. So hopefully, you guys didn't lose too many of you guys. So basically, this is the project area. This is the ortho image from Virtual Surveyor, which is a software we use to kind of turn the drone data into a bit more usable product. So we can get our tins and our contours, our topo, basically removing the structure, the vegetation and stuff. And of course, this is a Westland Resources presentation about drones, which means we always have to talk either about a crash or a drone or a hawk attack. So this is the morning of that flight. Everything was going well. We had perfect weather. We had a great takeoff and landing location. It was a pretty short flight, and it actually finished the entire flight perfectly, and everything was going great until it wasn't. And the second the drone turned back to head home to land, our good old friend red-tailed hawk flew up out of the trees, and before we had a chance to react, it took us out of the sky again. So the drone did initiate an emergency landing, and we did land. This is the last view we had from the controlling tablet. We saw where it went down, and we went and recovered it. And yet again, that EB is an amazing machine. It has had a couple of emergency landings, and every time it has one, it is flawless. This thing landed in an unpopulated courtyard and had absolutely no damage. So a bit of a side tangent, but I can't talk about this project without mentioning the fact that a drone or a hawk took our drone out of the sky yet again. So always a challenge, those hawks. Anyway, back to the map. We're going to focus on this small little section here where that red square is. So the surveyors here wanted some more information on some hardscape in this project, specifically this little bridge and the culverts that ran underneath. And we had the idea of using Lidar to help out with that. And this is why. So here's that zoomed in section. And we're looking at that bridge. You can see it, the wash kind of going underneath the bridge and where those culverts are. So where all that water is going to drain and be directed underneath the road. I'm looking this is the DSM view, so the elevation model, just to have a different look at it. And you can see that next square is a section of the bridge that we want to focus on. So this is going to be a little corner we're going to look at pretty much for the rest of this presentation, and we're going to see how we're going to use Lidar to fix some of the shortcomings that David mentioned earlier from drone photogrammetry. He did a really great job explaining how structure from motion works and what its limitations are. And as he mentioned, you need to have identifiable patterns or structures. And in several cases, and this is one of those cases where we have some highly shadowed areas, and also we have sharp edges and vertical walls. And structure from motion does a great job with, dirt and flat and relatively flat areas or gradual changes in slope. But it sometimes has a hard time picking a good sharp edge or a good sharp line. And also if there's heavy shadow and there's no structure inside those photos and it can't identify anything because it's too dark, that algorithm, that structure from motion algorithm, begins to break down. So here is a slope view of that same section where we can clearly see where drone data doesn't really do a great job. It does a great job pretty much everywhere else, but here we can see that sharp corner just doesn't exist. We can't see exactly where that head wall meets the ground. We can't see where the two head walls intersect each other in that corner. And, it's all the lines are wavy, nothing is sharp. It's rounded off in that corner where that shadow is pretty dark. And our surveyors needed some of this information, and they wanted to see if there was some way we could supplement this drone data with something that's just going to work a little bit better on these man-made structures. So in comes mobile Lidar. Rather than using, we're not going to use traditional airplane-based Lidar or anything like that, or we're not even going to need to use your standard terrestrial Lidar, which is on a tripod and has, those are very expensive and very time consuming. So we just jumped for a mobile Lidar unit. I'm sure a lot of you guys have seen this before. They were at previous GIS conferences. So this is the Zeb Horizon. We rented them from Allen Instruments. I think they're out of Phoenix. And anyway, yeah, so we rented it for a week. We had a couple of different projects that we wanted to use it on, and this was one of them. So we took this thing out to that little section, and this is what we came back with. These things don't need much training at all. Pretty much anyone can go out and walk this thing, and we did for only 20 minutes. That's all the time we needed to get all this information. So we, while we were out there, we also did have some aerial targets and other control points that we picked up with that unit. So there's actually a little base plate that goes on the bottom of that LiDAR unit. You just got to stick it down. Oh, someone said they've lost me. I'm not sure if that's the case or not. Okay, so maybe people can't hear me fine. Anyway, so here's another view, just looking more closely at that bridge, and you can see all the detail. I mean, it's just incredible how crisp and clear everything came out. Those sharp head walls, the culverts that run underneath the road, you can see everything. I mean, you can never get this view from a drone, at least one that's taking nadir images. Even if you got down and you took some obliques with the drone, you're just not going to get this level of sharpness and cleanliness out of a drone. And that's okay. I mean, that's just one of the drawbacks that you have to be aware of. But we thought it'd be interesting to see if we could take this data set and merge it with the drone data set. And so that's kind of the whole point of this presentation, is going to be, how do we get this mobile LiDAR data to fit with our drone data so we can process it all at one time and in the same environment. So this is the GeoSlam Draw software. So this comes with the GeoSlam rental for a week. And those little blue control points, those little blue points you see, there's 3 clusters of them. Those were where we set the LiDAR down on the ground to record the control points. So and asked about the range. It's about 300 feet on this particular unit we rented. So you can see our walking path because there's that high density of those LiDAR points. Anyway, we took these 3 points and we did a translation, rotation, and scale to bring this into the real world, bring it to the coordinate system of our project. So once we did that in GeoSlam Draw, then we were actually able to export that new point cloud that was aligned with our project in the real world. We brought it into Global Mapper. So, the same software that David was using, that blue marble software. So we had to make a surface model out of this. So we had to take it from a point cloud to a surface. Specifically a geotip is what we needed, because that's what Virtual Surveyor uses. So here's a nice little view. Again, just 3 different renderings of the same data set. Top one is an elevation model. The middle one is point intensity. And the last one is a color RGB. This one was actually made by overlapping the drone ortho and colorizing the point cloud with the ortho mosaic made by the drone. So we did that in Global Mapper. We didn't need to, but it looks neat. It's pretty cool. We needed to make an elevation grid, and we did that using a binning. The grid method we use is binning minimum, and so that gets you closer to a DTM. It is not a true DTM because, unlike true LiDAR, we don't have multiple returns. This ground-based LiDAR only has 1 return, so you're not going to go through Canopy or anything like that. You just get 1 return. So it's not, we can't get a true DTM, so we still have to do some post-processing. But this is that eye candy that David was talking about earlier. This is that surface model, that mesh. And again, you can still see that there's trees and stuff, so it's not a true DTM, but we didn't really need those portions in the desert. We were just looking at the bridge. So back to the drone digital surface model in Virtual Surveyor. That's what we're seeing here. And then inside that red boundary is the boundary of the Lidar data set that we processed, that Lidar surface. So here we go. I brought that into Virtual Surveyor, and this is what we got. You know, it's a totally different look. You can see all the culverts underneath the bridge, which is exactly what we wanted. And all we have to do now is bring that drone surface back. So when we overlay the two, we get a complete picture. So we have all the stuff that the drone captured, plus our section that we wanted to focus on with the Lidar. And now it's all in one place. So we can go ahead and we can take all of our ground points. We can create our contours and all the stuff we needed to do with one complete data set, but using two different tools. And so that's kind of that right here is kind of like the crux of the experiment, was that can we get these two to integrate seamlessly? And there's probably many different ways you can do this. This just happened to be the way that we chose to go about it. So let's go back and look at that bridge one last time and just get a closer look at this edge. You can see it's pretty sloppy. This is from the drone again. That's the structure from motion having a hard time resolving these details. Here it is with the Lidar. You can see those edges are crisp and clear. And again, with this corner, this is the same image you saw earlier. Here's that drone. And then here's with the Lidar. So it's just a night and day difference where we can actually confidently pick out those nice sharp edges, the tops and the toes. We can get all the points we need that you just can't get with the drone data. So I see this as a tool that is supplemental to the drone for the areas where structure from motion is the limitation. So if you have heavy vegetation or bridges or shadows or vertical surfaces you need to get, or any place with more low contrast, we can use mobile LiDAR to bring that data in and help out the drones where they simply can't produce the same results. So that's basically, I guess that's all the time I have. So thank you all, and maybe there's time for one question. But anyway, that's all I've got. Hope you enjoyed it.
So we do have a couple questions. What is the range of mobile LiDAR, and how close do you have to be to collect data? This particular model is 300 feet. Some are closer, some are further. But the closer you get, the more detail, the higher density the points will be. So if you're far away, the points will be very sparse because they're spread out over that distance. Then Mark asked, he didn't know you could rent them. So just to let you guys know, Allen Instruments, one of our premium sponsors, rents them out of Phoenix. Thank you, Jack. And I would like to point out that I was not the pilot or anywhere near the aircraft when the hot attack this time.
That was all me. And it was, I think it was, someone asked how much it was. I think it was $2,600 to rent. I could be wrong though. So you can check the chat later.
Thank you very much, Jack. All the presentations were great. I just want to let you know they will be available on the AGIC Symposium site under Speaker 2020. So if you want to go back and look at these at a later time. And I think that wraps up this SIG, and thank you for coming.
Good job, Casey.
Good job, Chuck. Wow, great. I enjoyed each and every one of those.
Yeah, they were amazing. I need to talk to Nick.
I want to rent one of those LiDAR cameras.
Oh, they're
awesome.
Fun. So much fun.
And you say
I have
just
so many things at my house.
Now you just walked around with that to get all that detail. Nothing else, huh?
Nothing else. Oh, well, we set ground control, and then you just
Uh-huh.
rest it for like a second, and it knows it stops, so it registers as a point. And then when you get in the software, you can put in the coordinates of your ground control, and then it moves everything.
Nice.
Yeah. So we've done quite a bit of work on interiors. We've scanned some mine buildings, and what else? Some culverts, lift stations. But I'm really interested in vegetation. Go fly with a drone, and then go underneath and get all the riparian, so we can get all the diameters of the trees, and track the growth of the years.
Yeah, that's yeah. Hey, in your opinion, how long before they put a Lidar in a drone? Like,
Well, they
seriously,
have them now. You can put this drone or this mobile Lidar on a drone. They have a mount for the matrix, so you can do it now. The thing
how
is,
heavy is it?
What's that?
How heavy is the Lidar?
Not sure. I mean, it's designed. They have a specific mount for the matrice.
Okay.
But you can mount that. The big powerful thing is when is it going to get small enough for like a regular quadcopter or a fixed wing can do it?
Right.
It covers huge amount of areas. So let's see what the weight on this one is. But no, it is pretty phenomenal. And we looked at it to actually get a drone, because it does single returns, but it does a cyclone motion, so you can penetrate canopy. You're not going to get every point to penetrate canopy. You can get quite a few points down to the ground because of the cyclone. Because the unit moves, the sensor moves inside, and then the whole housing moves 360 degrees. So it's a cyclone pattern that it sends out.
Wow. Amazing.
No, we're really happy with it.
Good stuff. All right. Well, I'll close this out and I'll see you at the next session, right?
Yep. Sounds good.
Okay. Thanks.